Good day. Today we will be presenting our project till Advanced Modulation Channel Access and Emerging Technologies in Modern Wireless Communication Systems. This presentation focuses on how wireless communication has evolved over time, especially in 5G and future 6G networks. We will explore important concepts such as modulation techniques, channel access methods, the role of artificial intelligence, and also discuss emerging technologies and challenges in next-generation networks. Wireless communication has undergone significant evolution, starting from simple 1G analog system to the intelligent and highly advanced 6G networks being developed today. This evolution is mainly driven by the increasing demand for higher data rates, lower latency, and the ability to connect a massive number of devices. In this presentation, we will discuss key technologies such as the advanced modulation techniques and multiple access schemes that improve network performance. We will also highlight how artificial intelligence enhance resource allocation and network efficiency. Finally, we will examine important challenges such as security, energy efficiency, and sustainability. Over the past few decades, wireless communication has rapidly transformed from basic analog voice systems into highly sophisticated AI-enabled networks. Each generation of wireless technology introduces new capabilities while solving the limitations of the previous generations. Today's networks are expected to provide high-speed data transmission, ultra-low latency, and reliable connectivity. These requirements are essential to support modern applications such as smart cities, autonomous vehicles, and immersive technologies like virtual and augmented reality. This shows how critical wireless communication has become in our daily life. The evolution of wireless system can be clearly seen from 1G to 6G. The first generation, which is 1G, only supported analog voice communication and suffered from poor quality and no security. Then 2G introduced digital communication and SMS, improving reliability but still offering limited data capabilities. The next one, which is 3G, brought mobile data and multimedia services, while 4G enabled high-speed internet and video streaming. Moving forward, 5G introduced low latency, massive IoT connectivity, and improved performance in dense environments. Looking into the future, 6G is expected to provide extremely high data rates, integrate artificial intelligence, and support advanced applications such as holographic communication. The continuous evolution of wireless networks is mainly driven by the growing demand for faster and more reliable communication. With the rapid increase in mobile users, IoT devices, and data-intensive applications, such as video streaming and cloud computing, earlier generations like 3G and 4G became insufficient. This network struggled to handle large volume of data and low latency requirements. As a result, 5G was developed to overcome this limitation. However, even 5G has its constraints, which is why 6G is being researched to provide even higher performance, better efficiency, and intelligent network management. 5G networks are designed based on three main objectives. The first is enhanced mobile broadband, or eMBB, which focus on delivering very high data speeds for applications like video streaming and virtual reality. The second is ultra-reliable low-latency communication, or URLLC, which is important for applications such as autonomous vehicles and remote surgery. The third is massive machine-type communication, or MMTC, which supports large-scale IoT connectivity. In contrast, 6G aims to go beyond these capabilities by integrating artificial intelligence into the network, achieving terabit per second data rates, and supporting futuristic applications like holographic communications. It also emphasizes energy efficiency and sustainability. Modulation is a fundamental concept in wireless communication. It refers to the process of encoding information onto a carrier signal by modifying its amplitude, frequency, or phase. The choice of modulation technique directly affects system performance, especially in terms of data rate and signal reliability. There is always a trade-off involved. For example, a higher order modulation schemes can transmit more data but are more sensitive to noise and interference. On the other hand, simpler modulation schemes are more robust but provide lower data rates. Therefore, selecting the appropriate modulation technique is very important. Binary phase shift keying, or BPSK, is the simplest digital modulation technique where each symbol represents one bit of data. It is highly robust against noise and interference, making it suitable for low data rate applications such as IoT devices. However, its main limitation is low spectral efficiency. To improve this, quadrature phase shift keying, or QPSK, is used. QPSK transmits 2 bits per symbol, effectively doubling the data rate while still maintaining reasonable reliability. Because of this balance, QPSK is widely used in LTE and early 5G systems. Higher order modulation scheme such as MCAM, including 16 QAM, 64 QAM, and 256 QAM, are used to significantly increase data rates. These schemes encode multiple bits per symbol by varying both amplitude and phase of the signal. For example, 64 QAM can transmit 6 bits per symbol, which greatly improves throughput. However, as the modulation order increases, the symbols become closer together, making the system more sensitive to noise and interference. To address this issue, modern wireless systems use adaptive modulation, where the modulation scheme is dynamically adjusted based on the channel conditions. Different modulation schemes offer different advantages and trade-offs. Lower order schemes like BPSK and QPSK are more reliable and perform well in noisy environments, but they provide lower data rates. On the other hand, higher order schemes like 64 and 256 QAM offer much higher data rates but require good channel conditions with high signal-to-noise ratio. This trade-off is often illustrated using a bit error rate versus signal-to-ratio graph, where higher order modulation shows better performance only when the channel quality is good. Therefore, adaptive modulation is essential in modern networks. In wireless communication, multiple users need to share the same spectrum efficiently. Channel access schemes are used to manage how these resources are allocated among users. Traditional methods like FDMA and TDMA have been replaced by more advanced techniques in modern systems. In 5G and beyond, methods such as OFDMA and NOMA are used to improve spectral efficiency, reduce interference, and support a large number of connected devices simultaneously. Orthogonal frequency division multiple access, or OFDMA, is widely used in 4G and 5G networks. In this technique, the available frequency spectrum is divided into multiple orthogonal subcarriers. These subcarriers are then allocated to different users dynamically. This allows multiple users to transmit data simultaneously without interfering with each other. OFDMA improves spectral efficiency and reduces latency, making it more suitable for dense network environments. Non-orthogonal multiple access, or NOMA, is an advanced access technique proposed for future 6G networks. Unlike OFDMA, NOMA allows multiple users to share the same frequency at the same time by assigning different power levels. At the receiver, a technique called successive interference cancellation is used to separate the signals. This approach increases the number of users that can be supported but also introduces higher complexity in signal processing. When comparing OFDMA and NOMA, we can see clear differences. OFDMA is simpler to implement and provides reliable performance with low interference, making it suitable for current 5G systems. However, it has limitations in supporting very large number of users. On the other hand, NOMA offers higher capacity and better spectrum utilization, especially in dense IoT environment. The trade-off is that NOMA requires more complex receivers and advanced signal processing techniques.
So now I will explain about AI-assisted resource allocation and self-organizing networks, or SON, in modern wireless network. As wireless system evolve from 5G towards 6G, traditional level-based network management is becoming less effective. Uh, this is because modern network must support very diverse services at the same time, such as enhanced mobile broadband, ultra-reliable low latency communication, and massive machine-type communication. Because of this complexity, artificial intelligence is now seen as one of the main enablers for this to be uh, for the future wireless system to be implemented in the future. One major advantage of AI-assisted resource allocation is that um, it no longer depends on reactive control. Instead, it can become more predictive and adaptive. In other words, AI allows the network to learn from traffic patterns, interference, and channel conditions, then decide how to allocate the resource more efficiently. Uh, this will, of course, improve the user experience while also reducing the unnecessary workload or waste. In AI-native 6G networks, intelligence is expected to be embedded throughout the network. This includes components such as AI-native intelligence, core intelligence engines, distributed edge learning, self-evolving protocol stack, semantic communication, reconfigurable intelligence surfaces (IRS) or RIS, and in edge intelligence. Together, these elements allow the network to perceive, learn, reason, and adapt in real time. Another closely related concept is self-organizing network management tasks such as configuration optimization and fault recovery in 5G, especially 6G. Networks are becoming denser and more complex, so automation is extremely important. In summary, AI-assisted resource allocation and so on are important because they help future networks become more intelligent, adaptive, and also reliable in highly dynamic wireless environment. Next question. Now I will move on to the some emerging technologies that are expected to shape 6G systems. Several technologies are receiving strong attention in 6G research, especially terahertz communication (THz communication), ultra-massive MIMO, intelligent reflecting surface (IRS), um, combined neural network. Okay, so these technology are important because future 6G systems are expected to support extremely high data rates, better spatial capacity, more reliable coverage, and also more intelligent radio environment. First, terahertz or TNZ communication. TNZ communication is considered one of the most promising technologies in 6G. This is because TNZ bands offer a very large amount of available spectrum, which means they can potentially support data rates from hundreds of gigabytes per second up to even terabytes per second. So this makes THZ communication very attractive for data-intensive applications. However, THZ communication also comes with major challenges such as high propagation loss, atmospheric absorption, and sensitivity to blockage. So while THZ communication is extremely high speed, it is much harder to deploy reliably uh, compared to lower frequency systems. The second technology is ultramassive MIMO. This can be seen as an extensive of massive MIMO from 5G, but with much larger antenna arrays, especially for high-frequency bands such as THZ. Ultramassive MIMO can significantly improve spectral efficiency, and also beamforming precision, and even the sensing capability. However, it also introduced technical challenges such as the phase noise, such as the channel sparsity, the mobility issues, and increased transceiver complexity. The third technology is Intelligent Reflecting Surfaces or IRS. IRS makes the wireless environment itself more programmable because instead of depending only on transmitter and receivers, IRS uses a smart reflecting system because from one channel it can reflect to IRS, and IRS will actually uh, increase the distance of the channel. But this can improve, of course, this will improve the coverage, reduce blockage effects, and also enhance the energy efficiency. Overall, this is the three technologies complement one another. The ZTHZ communication offers extremely high bandwidth, ultra-massive MIMO, improved spatial multiplexing and beam control, while IRS helps solve coverage and blockage issues by intelligently shaping the radar environment. Uh, next, next, we'll move on to the challenges in 6G network. So, although 6G promises major improvements in speed, intelligence, and connectivity, and so on, it also introduces important challenges such as security, energy efficiency, and also sustainability. First, security. Security becomes a bigger concern in 6G because future network will support critical applications such as autonomous transportation, industrial automation, smart infrastructure, industrial automation, and so on, and etc. etc. At the same time, 6G is expected to rely heavily on AI, edge computing, massive IoT, and so on. This means that threats such as unauthorized access, DOS denial of service attack, data manipulation, and model poisoning uh, will become more prone in the future. Because of this, traditional fixed-wheel security mechanisms alone are no longer sufficient for 6G. At the same time, AI native networking can also be part of the solution. AI-based security system can support anomaly detection. So this this modern problem requires modern solution. So if we want to use AI in 6G, we need to use AI in the security. So the next challenge, of course, the energy efficiency. 6G is expected to involve dense deployment. So high frequency technologies like KZ and also ultra massive MIMO, all of this can consume a lot of energy. Therefore, energy efficient radio access uh, need to be uh, properly designed in the future and to prevent the future networks from becoming too power hungry. Finally, sustainability. Sustainability is not only about reducing energy consumption, it also includes reducing the carbon footprint, improving hardware efficiency, considering the life cycle impact, and so on and so on. In other words, sustainability must be built into 6G from design stage rather than being created as an afterthought. So to conclude, so overall, AI-assisted resource allocation and SOM help make the network more intelligent and adaptive. Emerging technologies such as DHZ, alternative MIMO, and also IRS expand the capability of 6G in the future. These areas together show that 6G is not only about faster communication, but also about a smarter and more responsible network design. I think that's all for me. Thank you so much.